Good day to everyone. I'm going to present a large-scale laboratory testing of ballasted rail track and influence of artificial inclusions on track behavior. I'm S.K. Navaratnarajah, a senior lecturer at the Department of Civil Engineering, University of Peradeniya, Sri Lanka. The other co-author of this paper, distinguished Professor Buddhima Indraratna, at the University of Technology, Sydney. He's also the Director of Transport Research Center at University of Technology, Sydney. Starting with the introduction, rapid population growth and increasing congestion in highways in many countries, many cities demands for fast and heavy haul trains. Whenever there is a fast and heavy haul trains, then the track see a lot of high kinetic energy transferred to the track, and ultimately it reduces the longevity of the track. So if we don't improve the track system for this larger heavy haul trains and fast trains, this ultimately leads to excessive lateral deformations, vertical and differential settlements, and ballast degradations, and that leads to ultimately the derailment and accidents. Generally, this the rail track we have is commonly two types. One is called the open track, where we have a regular rail sleeper, ballast, sub-ballast, and the subgrade system. Then there are some isolated track where the tracks running on top of bridges or tunnels. This ballast is directly placed on top of a very stiff concrete type of a material. So these are the typical two types of tracks. It is important to understand how these wheel loads are getting transferred to the subgrade layer from the wheel through the rails, sleepers. Then we have ballast layer, sub-ballast, and the subgrade. Out of these different layers transferring the load to the subgrade system, the ballast layer is one of the important layer where there are many advantages of having that layer, and that very well distribute the load to the subgrade system in a minimum level. So it is very important layer, and whenever there is a fast heavy haul trains, this layer get damaged very quickly. We need to save this layer for a longer longevity of the track. In conventional geomaterial testing, we have this triaxial testing apparatus, direct shear and permeameters, where we can test soils like a clay to something like a coarse grain sands. These are typically for available in many laboratories. But this ballast material, which is used in rail track, the particle sizes are going from 20 to 65 millimeter. The conventional testing apparatus won't fit for this type of a material unless we do some kind of a size reduction or a parallel gradation techniques. So the solution for this one in terms of this testing apparatus is go for large scale testing apparatus. The first apparatus is the large scale direct shear test apparatus available at the Department of Civil Engineering, University of Peradeniya. We custom made this one considering the particle size in order to avoid the boundary effect. The sizes of this apparatus were chosen: 400 millimeter diameter and 300 millimeter high. Can be test ballast like a material, large size material without reducing these sizes. Then the second apparatus, the state-of-the-art process simulation prismoidal triaxial apparatus available at the University of Wollongong, Australia. This special machine having some special features. We can simulate a unit cell of a rail track under this testing unit. This machine has a capacity of 100 kilonewton It can run up to a frequency of a 40 hertz cyclic loading. The other special feature of this machine is the independent movable vertical walls on the 4 sides, where we can simulate the realistic rail track boundary conditions in the laboratory. You can see here on the right side, there are the triaxial box samples we have placed inside the triaxial box, compacted to the real track compaction level, and the slipper and the rail system is placed on top of that to place and test the ballast layer. This apparatus is having a size of 800 to 600 by 600 millimeter in the cubical size. Let's I quickly go through some of the results we obtained from these large scale apparatus. First one is the shear behavior of ballast, and also the influence of the rubber pads. As I said before, whenever the train speed increase and the load increase, it is going to damage this ballast layer significantly. One of the option to save this material is placing rubber pads. On top, we call it under slipper pads, and the bottom we call it under ballast mat. The under slipper pads are used, glued with the concrete slippers. Then we wanted to check how the shear is going to influence whenever we use the under slipper pads. This test result shows that the shear resistance of the ballast rubber interface is comparatively lower compared to the fresh ballast or the ballast to concrete interface. However, that we observed this rubber material is reducing the ballast degradation in a significant level. The fresh ballast itself have enough shear resistance, so reducing shear resistance by this rubber is not a problem. But by reducing this the degradation of ballast, we can save a lot of money saving this ballast layer. And this is the cyclic load testing using the process simulation apparatus. We tested the ballast for 25 ton, 35 ton XL loads. The frequencies ranging from 15 to 20 hertz. The result shows that the under slipper pad used underneath the concrete sleepers reduce the vertical and the lateral deformation, 20 to 30% of a vertical deformation and 10 to 15 lateral deformations. And also we know that the particle degradation is higher at the top level of the ballast because of the higher stresses. But whenever we use this under slipper pad, the rubber material, the breakage is significantly reduced. We can have like a more than 50% reduction by using these under slipper pads. The as I said before, the other type of a rail track running on a concrete bridges or tunnels, where this the layer below the ballast layer is very stiff. So in order to stabilize that interface, we generally use this under ballast mat. This is the options, the rubber pad placed underneath the ballast layer. So we tested this one under this process simulation apparatus, changing the load 25 and 35 ton. The frequency of the loading is ranging from 10 hertz to 25 hertz. The test results here also shows that significantly reduce the vertical about 10 to 20% reduction, and the lateral deformation reduced by 5 to 10%. And the degradation also significantly reduced, 20 to 25% at the top, and the middle is 30 to 50%, and the bottom is 50 to 60%. The bottom is the place where it directly in contact with this concrete layer, the concrete material, but by placing the rubber pad, it reduces the degradation significantly. And you can see here the ballast degradation is shown here. On the top is without the under ballast mat, the higher values are there, and with the under ballast mat, we can reduce the degradation significantly. The conclusions: large scale apparatuses are essential for correctly capturing the behavior of large size granular materials like railway ballast material. Normal stress and ballast slipper interface having influence on the ballast shear resistance and also the ballast particle breakage. What we observe is the shear resistance is reduced whenever we introduce this rubber layer, but the particle degradation is very small or comparatively lower when you introduce this underslipper pad to the concrete slippers. Then the increase of the axial load and the train speed shows that that increase the axial and the lateral deformation and also the degradation. But when we introduce the underslipper pad to the concrete slippers, we can see the reduction of vertical and the lateral deformation and also the degradation in significant level. And also this under ballastment placed on the top of the strip layer, that is also reducing the vertical and the lateral deformation and the degradation. I would like to acknowledge the Australian Research Council for the funding at the work done at the University of Wollongong, and the work done at the University of Peradeniya is supported by a head grant and also by the University of Peradeniya research grant. Thank you very much.